What's up, guys? You've heard the intro already. I'm going to actually just start this with like a really quick video summary of Peat that one of my good friends, Nate Lawrence, made because it's much better than I could do. And then after this, I'm going to kind of talk more about like the history of science that led to Peat and like supports his central thesis that is explained in this video.
Peat explained in around a minute. Dr. Peat was a biologist, philosopher, and painter. Ray's goal was to maximize energy production or metabolism and protect against stress. Dr. Peat's main thesis is that energy and structure are interdependent at every level. This applies not only physically, but spiritually, and this is what makes Peat's work so extraordinary. Maximizing the flow of energy is what gives us drive, allows us to gain autonomy, heal from stressors, and ultimately expand consciousness. In Dr. Peat's view, impaired energy production is the sole cause of disease and degeneration. When your metabolism is high, you burn more carbohydrates than fat. Burning more carbohydrates produces more ATP, consequently supporting the metabolism, and burning more fat produces less ATP, consequently lowering the metabolism, since most of the time that fat is the inflammatory polyunsaturated fat. Ray believed that polyunsaturated fats, which are essentially seed oils, are what have caused all of the degenerative conditions by impairing metabolism. As Ray famously said, keeping the metabolic rate up is the main thing, and there are lots of ways to do it. Essentially, you want to only eat things and only do things that increase energy production or metabolism. And the best way to measure metabolism is your temperature and pulse. Upon waking, your temperature should be around 97.5 degrees Fahrenheit and rise to around 98.6 in the middle of the day. The pulse of healthy populations should be anywhere from 60 to 100 beats per minute. If your temperature and pulse are consistently low, this is a sign that your metabolism is low. And if temperature and pulse fall after eating breakfast, this is a sign you're running off of the stress hormones, which we want to avoid. Energy production requires resources, and for most people, this means a gram of protein per pound of body weight and high-quality whole food sources such as grass-fed red meat, shellfish, eggs, and dairy. Pure muscle meat is rich in the inflammatory amino acids, tryptophan, methionine, and cysteine. So balancing muscle meat with gelatinous cuts of meat or gelatin powder can comprise about 30% of protein intake. Anywhere from 250 to 500 grams of carbohydrates is good, preferring simple sugars rather than starches, since starches can impair digestion and energy flow. Ripe fruits, fruit juices, raw honey, cane sugar, or table sugar should be consumed. Since sugar is not actually the enemy, the things that impair metabolism are the enemy. Well-cooked potatoes and white rice, both eaten with saturated fat, can also be tolerable. But listening to how you feel is the most important thing. This is the whole idea of peating, to perceive, think, and act. Balancing all meals with the protein to carbohydrate ratio of around 1 to 2 is a good measure to keep in mind. This allows blood sugar to stay relatively stable and helps nutrients to be digested and assimilated. Saturated fat should be the preferred fat, since it's anti-stress, structures cells, and offsets PUFA. 60 to 120 grams is a good range. Butter, coconut oil, which also further increases the metabolism, authentic extra virgin olive oil, and ghee are good sources. Grains, beans, nuts, and seeds should be highly avoided as they're not easily digestible and impair energy production. Chicken, pork, salmon, tuna, and other high PUFA foods should also be avoided since they impair energy production as well. Modern diets are high in phosphate, which is inflammatory, and should be balanced with calcium, which calms the cells and is overall anti-stress. The ratio of calcium to phosphate of around 2 to 1 is good. Calcium is also good for inhibiting excess iron absorption, which is also another issue of modern diets. Milk, cheese, and ice cream are rich in calcium and provide a balanced source of nutrients that can literally comprise a large part of the diet. Ray also believed heavily in coffee for its benefits to metabolism and overall health, seeing caffeine as a vitamin-like substance. As long as coffee is consumed with enough nutrients, such as with a meal, milk, heavy cream, and/or sugar, then it's good to consume. For its benefits to gut health and hormone balancing, insoluble fiber such as Ray's carrot salad consisting of 1 carrot grated lengthwise, 1 tablespoon of coconut oil or extra virgin olive oil, 1 tablespoon of white vinegar or apple cider vinegar with a pinch of salt can be eaten daily for its antibiotic and antiseptic qualities. Supplemental foods of liver and oysters should be consumed once or twice a week for their rich vitamin and mineral content. Occasional well-cooked greens can also be good. Supplemental magnesium, fat-soluble vitamins, B vitamins, ensuring adequate salt intake, and micronutrients are also other factors to keep in mind. If from diet and lifestyle alone temperature can increase, supplemental thyroid hormones should be considered. The Peat community on Twitter has plenty of resources, and the Peat forum is full of discussions surrounding Ray's ideas. Looking up anything you're interested in, followed by Peat, is a great place to start.
Yes, there's a lot of information there. If you want to double click on any of that, feel free to talk to me after. I think it's like really profound that so Peat, he was like a researcher for aging like back in the 70s after starting like a career in literature. So he like came to aging biology after studying basically William Blake as like a poet. And he was like one of the first people to talk about the dangers of seed oils and had all these countercultural ideas like that sugar might be good for you and that maybe we shouldn't be having like letting all these companies put toxins in our environment like way back then before anyone was talking about it. So if you're trying to trace back like the lineage of the current ideas, like a lot of them come back to this guy Peat. But yeah, I want to talk about like the scientific influences that kind of drove Peat to all of these ideas and how he was like so ahead of the curve. And I'm going to do this in the order of biogenesis, take you on a journey from how life might have started all the way to like how organisms work. So the core thesis that was stated in that video that Peat has said many times is that energy and structure are interdependent at every level. And when he says every level, this like literally means every level. So at like the cellular level, energy and structure are interdependent. At the societal level, energy and structure are interdependent. At the cosmic level, every level. So this is like not just a commentary on biology, but also on society and like complex systems in general. So I'm going to start with just the very beginning. Like how do I think and how does Ray Peat think life formed on the planet? So everybody kind of thinks in like the mainstream biology and the mainstream textbooks that probably DNA and RNA were the first things to exist, like nucleic acids, because there's this whole idea of this central dogma of biology where information is stored in these kind of information-containing molecules, DNA, RNA, and then you can only extract that information and give it to proteins, and then it can never go back around. However, this has come into some serious issues because when people try and replicate life's activities just from things that existed before biology, just like rocks and dust and stuff in the universe, people are rarely able to actually get kind of these stable, self-replicating like life forms that we know today, right? Like they can get maybe some levels of like reactions or catalysis, but not much. But there's this person, Sidney Fox, who is not taught in textbooks. Barely anyone knows about this guy, but he created basically what I'd see as cells from scratch. So what he did is he took amino acids, which were already found on the Earth in like these prebiotic times, back when everything was all molten and or starting to kind of cool into crust and everything. And he just heated them up and then he cooled them down. And then after he cooled them down, they turned into proteins kind of spontaneously with like some weird side chain modifications. And proteins are kind of the core machinery of life. And then they didn't only turn into proteins, they all condensed into these spheres called microspheres that are imaged here that are around the size of like small bacteria and were all around like uniform size. And these could do basically anything. They could self-replicate, they could synthesize peptides, they could synthesize polynucleotides like DNA, RNA. They could catalyze reactions. They had hormones that they could pass between each other. They could even do like basal cognition in a weird way. So you can like stimulate these electrically or put them in certain like ion gradients and they'll spontaneously have action potential. So that means if like a neuron fires, what there is like an exchange of salt with the external environment that kind of is a big peak and then it goes back and there's an electrical change associated with that. These microspheres, which was literally just heated up rocks that you cooled down with like some special conditions, they could fire electrically in a similar magnitude as neurons these days and propagate these firings across the different microspheres. So it's possible that there was cognitive life before there were even cells. And this is like, there's one jump that you have to make between this and like the current model of cells where somehow at some point these self-replicating microspheres had to pass off their information from like the proteins inside of them to some nucleic acids and then get the information back out, right? There was like basically one step that's left, but they've done all of life's activities and you could make possibly even multicellular organisms out of these microspheres. So then going back to the thesis of like energy and structure interdependent at every level, the reason why this was able to happen is because Earth was like a very energetic place and there was just stuff around and then spontaneously these complex structures formed and life was honestly pretty easy to make if you consider this to be life. So then moving on from that, after you have life, here comes a early 20th century, late 19th century Russian biogeochemist. So he talked about this concept called the biosphere. And the idea here was that, this is like kind of some of the first thought that the Earth wasn't just this like material rock everywhere that was inert, and then life was this like separate privileged thing. Life was kind of continuous with this surface and with like the gases around and the water around, and the metabolism was basically shared with the entire Earth. So what that means is that if you add these microspheres into a planet, you add like some really basal life, well, they start to have complex behaviors that create complex molecules that maybe trap some more heat in and then raise the temperature and then allow for more complexity and allow for more flow of energy and template more like life forms to start. So there's this like self-reinforcing kind of cycle that occurs once you start to flow a lot of energy over something. Like complexity emerges and then stabilizes itself and then creates more complexity over time. And then eventually Vernadsky with this idea went on to the idea, some really like revolutionary ideas that are kind of really pertinent today. Like what idea was like the noosphere that he was thinking about, where kind of consciousness, instead of just this complexity process that's like increasing because of biology interacting with like the matter around it, he thought that consciousness and thoughts eventually were going to drive the metabolism of the planet and drive the way that the planet looked. And we're seeing that now with just maybe we're all going to be paper clips pretty soon because of AI. I don't know. And then just a fun fact, he was like really ahead of his time. He realized after seeing that like energy creates structure just from like the sun coming onto the earth, heating up water, bringing water up and creating rivers that were like really complex in structure, creating life. He saw all this structure being created from energy. And then he realized around this time the energy contained inside of atoms. And this was like in 1910. And he was like, oh my God, there's like a huge amount of energy that we know because of our radioactive measurements that we have at the time in these atoms. And future societies are going to be able to harvest the energy from these atoms. And then he started kind of riding around Russia on horseback trying to mine uranium ore, and he was scared that the world was going to blow itself up in a nuclear war, and in 1910. So then okay, now we have like this world. It has like a shared metabolism everywhere. We have life. We have microspheres. They're made out of proteins. This was one of the most astute students of proteins. His name was Albert St. Georgi. Albert St. Georgi, he discovered vitamin C. He discovered how muscles contract and have these like molecular motors. And he was very against the idea that biology was just these kind of reactions in a test tube, but like really condensed together into this maybe like fatty balloon-like substance. He was really against that idea. He thought that life was much more coherent and much more structured than everyone expected. So he thought of protein as semiconductors. As semiconductors are basically these materials that are insulators, and then if you kind of pump enough energy, there's electrons that can conduct around. And he thought that life was kind of like a semiconductor, where if you're in this like pathological state and then there's like no electronic conduction, or like the electrons just go randomly and then create these damaging molecules in the environment. But in like a high energy state, these electrons could conduct and you could do metabolism. And that's what metabolism is. It's conduction of electrons. You could do metabolism and you could, do all of life's activities. So then he expanded this idea and thought about structure as the necessary kind of requisite for life. He thought that water was in this liquid crystalline structure around these semiconducting proteins, which is like a very solid state physics concept. It's like an LCD display with these like solid state semiconductors moving things around. And the second that it stops, being in that state, you get stuff like cancer. So like electronic biology and cancer. So again, energy and structure, you can't separate them. And then later, kind of building on some of these ideas, slightly after, this is 1960s, there was this man named Gilbert Ling. And Gilbert Ling, he really countered the general idea that was still pervasive even after Albert St. Georgi won the Nobel Prize and thought of life as a very structured thing, that, life was kind of just this like water balloon, like cells were just these water balloons that if you poke, they all like leak out. And you have to, they're kind of like leaky, so you kind of have to just like keep pumping water into the water balloon to make it not just like deflate and keep pumping the stuff that you want in. It's like an active, just tedious process. But he thought that life was not like a water balloon. He thought it was more like Jell-O. So if you think about Jell-O, all I do is I take gelatin, which is like a protein, and I take like this much water. I take this much gelatin, and then I mix it together, and then it turns into this like almost solid like gel, but it's made out of water, right? So how is it not like leaking everywhere? Well, it's because the water is associating with the proteins and forming this structured environment. And proteins are like uniquely suited to do this. So Gilbert Ling thought that in this kind of Jell-O, you didn't need to maintain structure by constantly like replenishing energy and doing this like active process of like putting everything back together. He thought of life more as like a state than a process, where there was this like high energy, low entropy state with almost structural energy that could be tapped into. And if you unstructure the life temporarily, that's the life's activity, right? So all of like muscle contraction, for example, is associated with the melting of the structure of the cell water inside the muscle as it excites. So life's process is reversibly losing and gaining structure back and forth. And that was kind of the innovation of Gilbert Ling. And this work actually led to the creation of the MRI. He inspired Raymond Damadian to make the MRI. And then there was, going through a lot of people here, James A. Shapiro. James A. Shapiro, he is still working. He's this guy who's has like a 21st century agenda for evolution. He doesn't think evolution is like a simple Darwinian process where there's just random mutations. Basically, it's been known in like many cases that organisms can kind of rewrite their own genome. So like E. coli, for example, like bacteria, if you just put them under heat stress, they start soaking in DNA from their environment to desperately try and get like a new gene to deal with their stressors. This actually has been shown to happen in so many more organisms than just E. coli. There's even evidence in mammals. So one example is there's this protein called an ARC protein, which is this virus capsid. It's just like a viral envelope that can be transferred between neurons and transfer genetic data between neurons. And it's known that this is from viral origin. There are no like previous steps, and we've identified similar viruses that this is from. There's also this protein called syncytin, where it's a protein that connects the placenta to the rest of the animal, and it's also from viral origin. So like viruses are kind of like the app store for the genome, for evolution. And like there are all these mechanisms to just like rearrange your genome and change everything intelligently in response to your environment. So the idea here is that like evolution isn't even just this random process. There's structure even in evolution and individual organisms trying to evolve. It's almost like the teleological idea of evolution, that there's like a purpose that it's trying to get to. And, you know, nurture is much better than nature in this respect, that genes aren't that important. The organism will use its genes to figure out the problems in its environment. And then kind of bringing this up, so we have like all these ideas of, you know, structure and energy are completely interrelated. Even at the levels of genes aren't that like important compared to like the environment that the genes are in. The structure of the genes can change in response to the environment. How does this like even relate to an organism? So then if you take this paradigm and then you bring it all the way up, if you're like, okay, all my cells are working together, the energetic state of all of my cells in my body matter, how do I kind of maximize my energy? And like, should I maximize my energy? So that's where the work of this man, Hans Selye, who's like an endocrinologist, comes in. So he kind of came up with this idea of this general adaptation syndrome. So he thought the root of most diseases was the body's hopeless attempt to regain energy and regain structure. So if you put a body through stress, you get these transient signals like cortisol or adrenaline that will increase your fatty acids in your blood, increase your glucose in your blood, give yourself like a shot of energy really, really fast to deal with the stress. But then if the stress is chronic, then you eventually start to just break down your muscles, break down all your glycogen. You end up running out of substrate to keep yourself in this higher energy state. Or if St. George's coherent structure in the cell breaks down, then you're just taking this energy and using it to destroy things, right? So then Hans Selye found that in the short-term stressors, and by stressing out rats and mice, he found that short-term stressors can raise energy, but over time you lower the energy production and you end up getting all these degenerative diseases from stressors. So like the logical conclusion for all of this is that if you want to, you know, be healthy, you should find a way to kind of increase your energy, increase your structure over time, and avoid stressors, and do it in a very sustainable way, rather than like relying on, you know, if you want to burn fat, like relying on a bunch of adrenaline to do so. You know, maybe take it slower and try and like, you know, yeah, like just not be stressed. So then, yeah, all of this like builds together to Ray Peat's ideas, everything that you saw, all the dietary recommendations in the first video, that like energy and structure are interdependent at every level. And the best way to approach this is to, you know, avoid toxins, try and raise the metabolic rate to maintain the structure of your body. If you lose structure, you end up getting things like cancer, which we know on MRI to have lost all their water structure inside of the cells. And there are many ways to do this. And the best way is to just like see how you feel. Even things that people tell you are going to raise your metabolism over time can become stressors if you are running out of substrate or your body is not in the right, you know, prime state to do that. And I think like he has hundreds of articles on his website, like raypeat.com. There's a ton of literature out there all around this, you know, many books that every one of these scientists have. And I have a website called literature.bio where you can just download these books for free online. And but I think like the pinnacle of his work is the carrot salad. So the Ray Peat carrot salad, this is peak. So one carrot peeled lengthwise, a tablespoon of coconut oil, a tablespoon of vinegar, and a pinch of salt. And Ray Peat thought about this as a paintbrush wiping your gut clean and removing the toxins from your body. But many people don't know this, but there's actually constant exchange of like hormones between your body and your gut. So if you don't have enough like bowel movements and things taking hormones out of your gut, you can get the things like estrogen overload or kind of stress hormone excess just because you don't have the excretory pathways. So I found a lot of people have had success just starting with this and then typing Ray Peat into Google. And yeah, my Twitter is Anabology if you want to learn more. So. Just
tell us what the honey diet is?
yeah. So there was all of this animal data. I was already primed with like Ray Peat. Ray Peat doesn't think sugar is bad. He thinks it's kind of like a inert substrate for energy. And like again, blocking the energy production is the problem, not the actual energy source. So I was like already primed to think that sugar is good. And I saw all of this animal data where animals were like restricted in protein. So they had like low protein diets and really, really high sugar diets. And for some reason, they were able to eat like 4 times the amount of calories and not gain any weight. Like there was literally a study where the authors fed mice Coca-Cola instead of water as their like, water source. And the conclusion of the paper was that, oh, drinking Coke raises your triglycerides. It's bad for you, right? But then if you look into their like raw data, the mice that drank the Coca-Cola ate 4 times the calories as all the other mice and ended up at same or like lower body weight than the mice who only drank water. So I was like, wait, why are these animals able to eat like so much sugar and not gain any weight? And I found like these papers that linked it to this hormone called FGF21, which is induced in like a low protein state. So I just thought that, okay, like what if I do some version of this with like pretty natural sugars? I'll just try eating like a pound of honey a day, like a a pound of honey a day, like a half pound of dates, and just like put that all in the morning, burn off all the sugar by dinner. And then, or try to burn it all off by dinner, and then eat a pound of protein at dinner, and then or a pound of beef at dinner. Go to bed, like redo that. And I raised my calorie intake from like 2,000, 2,500 calories a day to 3,500 calories a day. So I raised it by 1,000 calories every day, and over a month I lost 10 pounds. And that was like about a year ago. And I just like posted that online, posted my weight loss results, and eating more somehow and weighing less, and it just like has blown up from there. Like it hasn't gone away. It's been a year and a half, and people are still promoting it. I'm known as like Honey Boy, so I don't know. Yeah.
Does the amount of, you might have already said this and I may have missed it, but does the amount of fat matter when you're doing that? Like if you're raising your sugar, then you keep the fat relatively low?
Yeah, so I think it's definitely a lot easier to have success if you do like very low fat. There's this idea called the Randall cycle, and the Randall cycle is where if you add like sugars or fats to like an animal at the same time, you can like measure the rate of metabolism of either of those by like what enzymes are kind of upregulated. And basically fat can inhibit the utilization of sugar and carbohydrates. But I will say that this isn't known to be true for like every fat. It's possible that this was just like the fats that they used in the studies. Like maybe they gave them like seed oils or something. And maybe like my hunch is that MCT oil would work really well in this diet because it shares a similar like way of being metabolized as fructose. It just goes directly to the liver and is like quickly used for energy. But I've seen much more success like separating them out totally. And it's like I'm definitely experimenting more with like adding fats in DAOs. Yeah. Any other questions? Yeah.
I guess makes sense the recommendation to eat red meat. For me, like the recommendation not to eat fish is counterintuitive. For me, like cows evolved to eat grass for like thousands and hundreds of thousands and millions of years. We evolved to eat like a lot of animals. So I'm curious if you see the necessity to reconcile evolutionarily, like what we evolved to eat and what you would recommend, like not to eat fish.
Yeah. So I will say one thing about that. There have been these studies on Inuits in kind of say like the middle of Canada versus like very far north in Canada where there's access to like the ocean. And the Inuits that are in the middle of Canada, they generally would eat like big game, kind of like a moose or like wild like buffalo. And all of these have like saturated fats, right? And those Inuits are basically, there's like some genetic differences, but metabolically they're very genetically similar to people who were like in Russia or just like any other place in the world. However, the Inuits that were very far north, they had a diet of things like seals that were very high in omega-3s. And these Inuits, they have a mutation in this enzyme called CPT1A. And CPT1A takes fat and shuttles it into the mitochondria. So for some, and basically like their mutation makes the CPT1A non-functional. So we just know in humans for some reason that the people who have had the highest exposure to omega-3s in their diet naturally have created a mutation that disallows fat from getting into their mitochondria at all. And what that means is there's only one other place where you can really metabolize it, and that's in peroxisomes. and peroxisomes are this place that can handle like a lot more like oxidative stress and kind of junk than mitochondria specifically. So like what it suggests to me is that really high amounts of omega-3s will cause like pretty strong oxidative stress in mitochondria if they're being used for energy, like enough for a certain population to exclude them. Otherwise, they had like a pretty bad survival outcome. And like Ray Peat's idea around like fish oils and omega-3s is like basically the same, that they're very unstable molecules because they have a lot of oxidizable bonds. And you know, I think this really manifests in like high doses, where there were some mouse studies where certain, like it's progeria mice, so these mice that had accelerated aging, were fed a high omega-3 diet and they died much faster than control mice. But those are like very high doses, and like the really like lower doses that you get in, say, just eating some like normal salmon or something isn't nearly at that. And at that level, you probably don't get high incorporation into your cell membranes. You just get the anti-inflammatory signaling effects, if that makes sense. So like I think Ray Peat was kind of extreme on this, saying that you don't need any at all. I think like the more rational position, like looking at the data with like clinical trials showing better like mortality risk in cardiovascular disease when you supplement fish oils, is probably just don't do a mega dose, like do the low dose that they do in those studies, if that makes sense.
Yeah, thank you. I'll make all of the authors
Mm-hmm.
What's your response to someone like Ryan Johnson, who touts having low body heat? Like, what's going on there?
Yeah. Well, so there's like basically an association that has led to the idea that low body temperature is good for longevity, and its size. So like if you make an animal really small, they usually live like a pretty short amount of time, aside from like a couple outliers. And then if you make it really big, they live for a really long time, like elephants or humans or like whales. So then if you had like a fast metabolic rate and you were like an elephant, if you had the metabolic rate of a mouse and you were an elephant, the elephant would like explode immediately because it's just like too high. They can't let off heat enough. So then it's like pretty much impossible to decouple this from, like this association at least, from size alone. You know, and if you look at the examples where people say like, oh, this like one specific species has a very, very low metabolic rate, even among the animals of the same size, and it lives much longer. Like the notable example is the naked mole rat that has like a very cold metabolism, very slow metabolic rate, yet it lives like nearly indefinitely, like 30 plus years, but without any increased risk of dying. That is true, that this animal has a low metabolic rate and kind of like lives a very long time. But the kind of idea that people have is that slowing the metabolic rate stops the rate of damage accumulation. And we see in naked mole rats that they actually have more DNA damage, more oxidative damage than us. And then there's another animal that's at that same size that lives nearly as long, called a bat. And bats have a very, very high metabolic rate. And there's like two different strategies. So bats have a high metabolic rate, they burn really hot, they are very social animals, and they get like fevers when they get sick, and they try and kill every single cell that has a virus. But naked mole rats are like less social, don't have as much viruses around them, and they kind of just like let damage happen to them. So like to me, the low metabolic rate strategy is just like let stuff happen to you and hope that your body doesn't respond and kill yourself. And then the bat strategy, or like even the human strategy, because we're hot animals that are social, is, you know, burn hot, try and get rid of viruses before they kill you, and then maybe every once in a while your inflammatory reaction will accidentally kill yourself. But that's like the cost that you pay for being a social animal. So like in summary, I just think that it doesn't really apply to humans. It's just kind of like an association that like has not been validated interventionally.